Folks, we're back, and I left you with an example problem, didn't I? Did you do it? Probably not, but we're going to do it together now. And this example problem says, draw the structure for the following. And it gives me 2-phenylhexane, benzyl alcohol, 3-benzyl pentane, and bromo methyl benzene. Okay, so they're going to expect me to go through this and kind of give you a structure for each one of these. So how on earth can we do it? Well, we use two terms, and the two terms that we learned in the last video was this whole thing of phenol and benzyl. So let me draw both of them for you, shall we? Let's do it. Okay, so phenol is a benzene ring that's directly on a big longer chain, and benzyl with a YL is a benzene with a CH2 on a big long carbon chain. So we're going to have to use these two terms, and we're going to have to incorporate them into names at this point. All right, so let's start with our very first one. So our very first example said that we needed to draw 2-phenylhexane. All right, so did you do it? I hope you did, but again, you probably didn't, so we're going to do it together. I'm going to force you to do it. All right, so 2-phenylhexane. Hexane. All right, well, hexane is really an orgo-1 type of thing, right? We're pros. We're experts at this by now. So hex is 6. 1, 2, 3, 4, 5, 6. And ane means all single bonds all the way across. There you go. There's hexane. Well, I've put a 2-phenyl in the front. All right, so on the second carbon of the main chain, 1, 2, right there, we have a phenyl group. Well, I now know what that phenyl represents. The phenyl group is basically this benzene ring. So there you go. So the reason they did the main chain as the straight chain is because there were 6 carbons there. Benzene has 6 carbons. We go toward the longest carbon chain most of the time. But when we get to the 5 and 6 area, if I wanted to name this as a benzene structure and use benzene at the ending of the name, then we call that the parent name. How on earth do we name this group up here at the top? We cannot name this a hexyl group because that's a secondary, that's a secondary, that's a secondary, that's a secondary. So there's tons of different choices there. So it's going to be much easier if I name the longest carbon chain, 5 or 6 carbons. By default, it goes there. And then if there are benzene groups on it, we'll name those benzene groups as substituent names. So 2-phenylhexane. All right, so now let's look at our next one. Our next one is benzyl alcohol. Do you remember? That was probably one of those structures I told you had to memorize. All right, well, we don't have to memorize some of them now. We kind of know how the name gets originated. So benzyl alcohol. All right, well, what is the benzyl group? Oh, well, we just learned that. That's this benzene ring with a CH2 group hanging off of something. Okay, well, that's where you'll start. And what's the alcohol group? The alcohol group is OH. Folks, there's benzyl alcohol. It's as simple as that. It shouldn't be more complicated, right? All right, well, let's look at another one. 3-benzyl pentane. All right, so pentane, pent, well, that's 5. 1, 2, 3, 4, 5. If you don't know that, sorry, I don't know how you got here. All right, pentane, ane, all single bonds, single, 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 all the way down. And then on the third carbon of the chain, 1, 2, 3, right here, we have a benzyl group. Okay, well, what's the benzyl group? Oh, well, Tracy, you just told me this is a CH2 group and a benzene that goes off of that. All right, well, there you go. There's 3-benzyl pentane, and there's the structure. It's all you need. All right, finally, our last example that I left you with was bromo methyl benzene. Okay, well, benzene. Well, here we go. Ring around the rosy. Okay, there's benzene. And we have a bromo group. Well, bromo we know is Br. Hopefully you know bromo's Br. Again, if you don't, I don't know how you got here. And then methyl group is a CH3 group. So Br and CH3. Those are the components that need to go onto this benzene. Well, where do they go? Br and CH3, are there numbers in front of them? No, I don't see any numbers. Do you see any numbers? No, there's nothing written. So if there's no numbers there, they're understood to be a 1. It's in spot 1. So that basically is telling me that this bromo group and this methyl group is probably on the same carbon? Does that make sense? Okay, well, let's take a look. Well, there's nothing there for bromo, so I'm just going to put that as carbon number 1. And there's nothing there for methyl, so I'll do that there. And you probably walked away and said, here's my answer, and I'm going to go, eh. So the question's why? Why is that not correct? Okay, well, here's why. We're going to redraw benzene. Okay, so here we go. I'm going to put a double bond, single, double bond, single, double bond. I'm going to draw the double bonds out. All right, so what that means is that this carbon, if we chose that to be spot number 1, it already has 1 bond, 2 bond, 3 bond, and there's only one more spot. No more. Just one more bond available. But we've got 2 groups. So if you do this, what you're telling me is that this carbon has 5 bonds. And the reason it has 5 bonds, folks, is because benzene, because we get into the habit of drawing this circle all the time, we typically forget that there's double bond characteristic with every single one of these carbons. This carbon has a double bond characteristic associated with it. So there's already 3 bonds in place. We only have room for 1 more. That's it. We cannot load bromo and methyl on at the same time. But the way that this name is written, there's no numbers associated with it, which means that the bromo and the methyl have to go on to the same spot. So how do we get this done? Well, this was kind of a trick. Methyl is 1 carbon, so that's a CH2, and bromo is a Br. So this is a bromomethyl group. That bromomethyl group is attached to spot 1, and that spot 1 is that 1 carbon that only has room for that 1 bond because it's already tied up in a 3-way, folks. It's got no more wiggle room to break bonds and bring in different substituents at the same time other than 1. That's it. So this one was kind of a trick. If you did do these 4 examples, you probably screwed it up right here. And if so, that's okay. That's normal. You weren't bad. You did your job the right way. We kind of set you up and tricked you. And this is one of those examples where that happened. Okay, so now we've went through this discussion of nomenclature. Very quick, but we at least talked a little bit about how to properly name them. And the reason is because we're going to start doing this with all of the reactions that come along with benzene. All right, well, we're going to start off with benzene, and I'm going to be able to talk about benzene, and I'm going to be able to talk about reactions of benzene, and these will make products, and those products we will be able to name now. That's kind of how this all is going to start building up in the end. So what I've done here is that on the screen, I've drawn benzene for you, and up on the top is the resonance form of benzene, and down below is kind of the strict double bond characteristics that's associated with it. So in the world of benzene, we need to talk about reactions. Now, we're going to use what we know, right? From Chemistry 251. Orgo 1. What do I know about structures of organic? Well, let's talk about it. Number 1, we have a ring system. And a ring system really locks things into place. You know, if this was a straight chain, they'll be all flippity-floppity, and the bonds will be turning and spinning and doing all kinds of warpy little things. Okay, well, rings aren't that way. Rings are very structured. They're very, this is the way it's got to be. Okay? Well, that's benzene. It's in a ring. It's locked into place. Can't really do too much of anything, right? So another characteristic here is that not only it's a ring, but it is a 6-membered ring. Okay, well, 6 members. Well, how many members are participating? 1, 2, 3, 4, 5, and 6 in the ring. So when we started talking about cyclogroups in Orgo 1, we often start off with cyclopropane, cyclobutane, cyclopentane, cyclohexane, and then cycloheptane, cyclooctane, and so forth. Well, during that discussion, what you should have been exposed to is that due to how the carbon bonds are oriented, all of the bond angles, all of the bond lengths that kind of get incorporated into the structure, all of that information makes cyclohexane perfect. So 6-membered rings are very stable, folks. Very, very stable. A 5-membered ring, yeah, it's going to stay around, but it's not as stable as a 6. The 4-membered ring, no, there's a lot of strain on that cyclobutane group, and that cyclobutane ring is going to pop whenever it can. And then the 3-membered ring, the cyclopropane, there's even more tension on those bond angles. So that structure, not going to stay around very long because it's going to pop just like a volcano when it gets exposed to something. I mean, this is kind of the whole concept of epoxides, right? We said epoxides were very reactive because there's a lot of strain on it, and there's a 3-way love triangle that's going on, and they have to pop open, and they're very easy to basically get that to do or get that to happen. So 1, we have a ring. 2, we have a 6-membered ring on top of that. 3, we have delocalization. Okay, well, delocalization, double, single, double, cause you trouble. That's delocalization. So basically what that means is everything that we've talked about, delocalization really puts forward the aromaticity of benzene. It is an aromatic compound. So delocalization turns the kids loose out in the front yard. They just run wherever they want to run. They scatter throughout the entire subdivision, but they're going to be perfectly safe. We're not going to lose them. And then sooner or later, they might come back home. They might gravitate back to where their starting place was, but they're going to have the freedom to do whatever they want to do throughout the day. This makes the benzene molecule very happy because it makes mama very happy as well, and daddy probably too at the same time. So delocalization leads to this concept that molecules that are delocalized really have a increased stability whenever we see them. Maybe they're not as reactive. They're more stable. They're going to last a little bit longer for us. So, folks, the reason that I'm going over this is because we need to start thinking about reactions. And all of a sudden now, I'm giving you a plate. And that plate is 1, it's a ring. 2, it's 6 members. Very, very stable. 3, it's delocalized. That means it's very, very stable. And 4, because of the delocalization, we don't really have true double bonds, right? We draw them, but this is a resonance form, which means that this is close to what it is, but the hybrid is a better representation of that because it's not really a true double bond, but it's not yet quite a single bond either. It's kind of a hybrid. It's in between the two, which is why we call it a hybrid. All of this starts mounding up on your plate. And if you get to this point and you look at this structure and I say, is this reactive? You're probably going to say, maybe not. Just because of its structure. because of its shape, because of the delocalization, because there's not really true double bonds in the molecule, benzene is probably not going to be very reactive with us. And quite honestly, it's not. It's not. We are not going to go on and on and on about benzene reactions. However, it can. It can have a few reactions, and those few reactions we need to talk about. But benzene as benzene, nothing else on it, no other groups, can undergo 5 different reactions. And we need to talk about these. We need to work through them. Maybe a little bit of mechanism with them. But we need to get comfortable with the basics of the benzene reactions before we go further. Okay? All right, so let's kind of learn some vocabulary. Words! We're going to use our words. Benzene will undergo reactions, and these reactions are going to be called ears. It's kind of how I like to refer to them as. And this is electrophilic, aromatic, substitution reactions. Electrophilic aromatic substitution reactions. Woohoo! Whoa, doggies. We kind of already mentioned this, though, haven't we? Yeah, we did. The electrophile, nucleophile, pedophile. Okay, so electrophile means electron-loving. And electron-loving probably means something with a positive charge. This is not uncommon, right? We've always talked about positive charges. Think about all of the carbocations that we've talked about, okay? Carbocations happened all the time. What charge were they? Positive, because they were called cations. Aromatics. Well, look what we just did. We went through some lecture videos about what aromaticity means. What is an aromatic? Well, folks, you know the 4 criteria that's an aromatic now. So we're really focusing on ring structures that are delocalized, that are flat, and that all have sp2 electrons or configurations at those atoms. That's what aromaticity is. We now know that. Okay, well, the last word is substitution. And substitution is another Chem 251 topic that should have been covered. So substitution means you're dating somebody and you see somebody come through the bar and you go hubba hubba and you substitute your partner. You pair up with somebody else and you leave for the night and you never turn around and you never look back. What a shame. I hope you're not one of those people. That's what I always say. Don't be one of those people. Don't have a substitution reaction on a Friday or a Saturday night. So these electrophilic aromatic substitution reactions basically means something needs to get substituted off of the aromatic ring. Well, if we're only talking about benzene, I'm going to go ahead and draw the double bonds on here just so I can kind of prove a point. Each one of these carbons has 3 bonds in the ring. There's a double bond and a single bond associated with it. There's only room for 1 more bond, and that is it. And that 1 bond will be hydrogen all the way across. So there we go. There's our hydrogens. Well, the definition of this electrophilic aromatic substitution means something has to get substituted off the benzene. What is there to substitute? Hydrogen? That's the only thing hanging off of the ring is hydrogen. And ding ding, that's exactly what happens. So on this benzene ring, we have a vulnerable hydrogen. Actually, all of them are vulnerable, but we're going to only focus on one. And that hydrogen will get substituted. That hydrogen is on an aromatic, and this aromatic is benzene. So that hydrogen is on an aromatic, that hydrogen will get substituted, and that hydrogen will be substituted with something that carries a positive charge. And we get a reaction that goes forward if this is the general template that we lay out. And these are called the electrophilic aromatic substitution reactions. We can make a song out of that, right? So the issue here is that mechanism-wise, folks, it's pretty much the same. I mean, think about this. If we had a double bond, that double bond, whichever one it might be, is an electron source. And that electron source, folks, this is negative. What do you think is going to happen to that negative area? Oh, here we get a positive. And they fall madly in love, and a reaction begins to happen between the two. Now, does that mean that that double bond will break? And the answer is no. Because this is not an addition reaction. That's a difference. This is not an addition. If it was an addition, then we are adding this onto the benzene, which means that this double bond will break. Two sites of attachment open up, and bing, bing. Things go on to those sites. Things go on to those carbons. This is not an addition reaction. I don't see the word addition in the name. Do you? No. I see the word substitution. So that means that this hydrogen, or any of the hydrogens that I decide to pick, it doesn't matter, is going to go away. Shoo, shoo, fly, shoo. And then something else more beautiful, more handsome, comes into the room, catches the eye of the benzene, and that benzene says, "You're sticking with me." And then off goes that disposable hydrogen. I told you in Chemistry 251, haven't I always said, hydrogen gets the short end of the stick every single time. Every time something goes on, hydrogen is so disposable. They just abuse them, they trash them, they badmouth them, they kick them to the curb. You know, no one appreciates the job that hydrogen can do for them. Okay, a little bit of more nomenclature. This question mark, well, in this world of electrophilic aromatic substitutions, they like to use not a question mark, but a Y in the general template. So if you're flipping through a text, if you're flipping through reference material, that is really what they like to use for an electrophile, because again, this is electrophilic. So Y positive represents the electrophile that is needed to react with the benzene in order for this substitution reaction to happen. Now, I want to look at this in a little bit more detail because all of the 5 reactions that we're going to be talking about really follow the same model. All right, so I'm going to take a little bit of time, take a breather. We're just going to kind of coalesce around this template and then just assume that everything else pretty much happens this way with all of the 5 reactions that I'm getting ready to show you. So here we're going to redraw benzene, and I've got a double, single, double, single, double. And I'm going to react this with some type of an electrophile. And I'm going to start drawing curvy arrow mechanisms. All right, so the rule of curvy arrows back in Chem 251 basically said, you start with the arrow. And you start with the arrow at the negative. Okay, so that means you better not start the arrow over here. That's not the rule. It's never been the rule. That's a positive. Come on, I just said you start the arrow at the negative source. So the negative source is going to start at one of these double bonds. That's where my negative is going to be located. And then we point that always, this is what we've always done, we point it to a positive piece. So there's the first step of the mechanism. And this creates an intermediate. Why is it called an intermediate? Well, that's because this is not going to last. This is not our product. There's going to be something else that's going to be involved here. All right. So this double bond breaks. 2 sites of attachment open up here and here. And then we add on our electrophile. So there's the electrophile right there. All right. Now, you got to keep in mind this also had a hydrogen. We didn't draw it, but we could if we wanted to, right? That was the fourth bond. So that fourth bond is still there, but now I add on this fifth bond, and here this one doesn't get anything, so it just was removed some electrons from the bond because it went broke, and we get a positive piece that happens here. This was always the first step of the alkene reactions. There's no difference here. We have a double bond. The double bond broke. Two sides of attachment open up, one on the left, one on the right. The addition piece got added on, and then that formed a carbocation. Then that carbocation went another step, and we added something else to it, and that basically satisfied the need of the positive carbon. But hold on here. I thought you just told me that this was not an addition. It's a substitution. Well, it is. It is, right? You're thinking the right way, but I'm not quite done. So in the beginning, this does begin to look like an addition reaction. That's exactly what we've done here. We've broke a double bond characteristic. We've added something to that benzene. We have destroyed the delocalization network of the ring at this point. And we have formed a carbocation. Whoa, whoa, whoa. Did that make sense to you? If it did, you're learning organic, because that was a mouthful of organic that I just laid out onto the table and just served it right up, and you probably followed it the entire time. Okay, at this point, what do? Right? What goes on now? Well, it can't just be this Y positive. We know there's going to be something else. I can't just bring a bottle of something positive in and say, here you go, this is all that you need to use. It's probably going to bring in something else. And what they decide to do here is use the variable Z. And this Z is going to represent the counter component. All right, it's going to be negative. So if I bring in this piece, whatever this piece is, it's going to carry a negative charge. Again, we're just doing a template. That's all that we're doing. No real reaction yet. It's just the general template of the mechanism. So I'm probably going to have to bring in something negative into the picture. And there's two options here. The first option is that this negative can say, ooh la la, positive piece, and then it's going to sit basically on that carbon. Now, if that's what goes on, that's a problem. The reason that this is a problem is because this option, route number 1, destroys the delocalization that was there at one point in time. And we've already talked about the power of delocalization. We've already mentioned it. So if that happens, that molecule is going to be very disgruntled. It's not going to be a happy camper. It's not going to like you very much, because you have just destroyed something good that was going on. And it's in a worse spot now than what it was before. Could you imagine getting in a relationship with somebody and your life just gets destroyed just because of that person? That's what this benzene's going through right now. Doesn't want that. Too much drama. It wants to go back to the way it was, when it was happy, when it was just maybe by itself, when everything was okay. But that Z component really messed everything up. So the other option is that it is a negative, and we just brought in this Y component, and this Y component made this carbon now a little weirded out. So this carbon knows, hey, this Y piece came in, I had a hydrogen here, I had 4 bonds in total. You know, I could get back to that double bond if I could get rid of one of these things. But hydrogen is just so useless that out of these two choices, I probably can get something a little bit more out of the relationship with that Y component that came in, that positive electrophile. So hydrogen, you got to go, but I got to dump you somewhere. I'm not just going to leave you out on the street. I want you to actually have someplace to go. Well, that's this Z component. This thing that carries a negative charge, the second option that it could do is it could come in and attack the hydrogen and bloop, pop it off and say, hydrogen, you were never treated the proper way. If you came to me and lived with me and we had a beautiful relationship together, I would feed you grapes and fan your face every single day. And that hydrogen, okay, I'll do it. And then it leaves. Well, when it does leave, it leaves behind some electrons. Because look, there's a bond that's right there, isn't there? There's a carbon to hydrogen bond. So that bond is going to shove those electrons back into the ring. And what forms here is the reformation of that double bond. Nothing else of the ring got touched. And now this Y component is attached to that ring, not the hydrogen. That hydrogen has been ripped off, and that hydrogen has been ripped off by that negative piece that came in. In other words, a nucleophile at that point. So this is really why we call it a substitution. In the middle, it looks like an addition reaction because we break a double bond, but this is the middle stage. That double bond will reform, and that hydrogen will be released and will be substituted for the electrophile that came in. So what was a hydrogen here is now some type of atom, some type of ion, some type of an electrophile that we have brought into the picture. Folks, this is electrophilic aromatic substitution right there. So all of the reactions that we are going to focus on from this point in the beginning stages will undergo the same template. We'll be talking about what the Y positive pieces are. We'll be talking about what the Z negative pieces are. And we'll kind of muddle through those waters when we get to that point. But welcome to the intro of benzene reactions. So in the next video, we'll pick up from here and we'll talk more about these reactions and we'll identify them and maybe talk about a few of the mechanisms.